Okay, so today we're going to finish up Module 4, which again is on chemistry of the alpha carbon. So we're removing an H, substituting it through the different reactions. And then your exam will open today at 2:15, 24 hours to do it, and it closes tomorrow. Any questions on anything? What's the meaning of life? No questions? Okay. So we had ended last time on the Claisen reaction, which produces a beta keto ester. So for example, that's the product from the self-condensation of ethyl acetate. We have our alpha and beta carbons. The beta carbon is a carbonyl at oxidation state 2. These alpha hydrogens were more acidic. They had a pK of 10, and that allows us to use a weak base to deprotonate them. And so what we're going to look at is abstracting an H and then substituting it there. So in general, that's just a normal SN2 type reaction or an alkylation. So let me redraw that. So a key thing about this structure is that alcohol component of the ester basically allows us to use the conjugate base of that alcohol. So that plus sodium ethoxide allows us to deprotonate those alpha hydrogens pretty easy due to the pKa difference. So there's two different reactions that we'll look at to start with. One is called the acetoacetic acid, and the other is the malonic ester synthesis. The names here come from what you're starting with, not with what you're ending up with. So they can be a little bit misleading. The acetoacetic acid synthesis produces a substituted acetone. The malonic ester synthesis produces a substituted acetic acid. So both of those essentially react the same way. You're just starting with different functional groups. So the alkylation occurs through an SN2 mechanism. The active methylene group, that CH2 group, is the nucleophile. And so you have to match the electrophile to the SN2 trend, where a methyl reacts greater than a primary, greater than secondary, and then tertiaries don't react. So we'll start off with the acetoacetic acid synthesis. And as I said, that's making a substituted acetone. So acetone is the 3-carbon ketone. So propanone. We use acetone quite a bit in lab to clean glassware. I could probably drink a 16-ounce pint of acetone at this point in my life. It's relatively non-toxic. It's actually a byproduct of metabolism as well, so it's found in urine. So the starting material for this is that self-Claisen product. When you take the ethyl acetate, do the Claisen, you get the ethyl 3-oxobutanoate, and we're going to treat that with the sodium ethoxide. So we have those two hydrogens, so they're pretty acidic. I'll just sketch out a mechanism real quick. So that gets abstracted. And then we generate that enolate structure. And because there's two carbonyls, it can enolize in those different ways with the E and Z geometrical isomers. So the enolate, again, is supplying the lone pair for the SN2. And so we can react that with an electrophile, which I'm showing is this R1X. And the X is the leaving group. So if I circle that hydrogen H in the product, it's been substituted for R1. Now, if you look at that, how does that become the substituted acetone? So essentially, we have to get rid of this. So it turns out it's pretty easy to do that using reaction types you've seen before. So we're doing an SN2, then we're going to do a saponification. So that's a base-mediated hydrolysis of an ester to an acid, and then we're going to lose this carbon atom that I'm circling in red here. That carbon atom gets extruded. So once you've done the substitution, so there's your R1, you treat with sodium hydroxide and water. This is called saponification. And so if we look what's happening, that ester is getting substituted. So nucleophilic acyl substitution, which we talked about in the prior module. Because we're under basic conditions, we form the sodium carboxylate. Once the hydrolysis has completed, we adjust the pH with concentrated HCl, and then you heat the crap out of it to 110 degrees. And so now look at what's happening. This carbon that's bearing the R1 group still has the R1, but now it has two hydrogens. So it starts with one, it ends up with two. So how does it get the second one? And then where does this part of the molecule go? So that's the mechanism I'll draw out on the next slide, but everything else we've sort of seen already in terms of SN2 and saponification. So say we've adjusted the pH to this point. So we have the acid. So I'm just going to do a bond rotation. So I've just rotated around a sigma bond. And that sets up the following structure. And if you count the number of atoms starting from this hydrogen, there's 1, 2, 3, 4, 5, and 6. So 6 is that recurring number you see a lot in organic chemistry. So once it gets into that conformation, the heat will induce a loss of carbon dioxide. And we can show that with arrows. So that pi bond comes up to abstract the hydrogen. The OH bond will cleave. That's going to form a second pi bond to that carbonyl. and then this bond cleaves that way. So I'll draw this kind of bent so you can see where the atoms were mapping on there. But that's CO2, and so that's a gas that bubbles out. Yep.
What's the order of the cleavage? Where did it start?
So I typically start it from this pi bond because that is electron rich. So you can think of it as abstracting that hydrogen. And then this bond has to cleave, so it forms a pi bond to that carbon. And then this sigma bond cleaves, giving you a double bond here. So if you look, that's not quite a ketone yet, right? If I number those atoms in blue as 1, 2, and 3, that hydrogen atom on the oxygen will shift down to the carbon numbered 3. So maybe I'll stick in that hydrogen just so we can see it. The existing hydrogen tags along the whole way, and that you end up with 2. This type of relationship with this sort of forward and backward arrow, these are called tautomers. So I guess for the purpose of this class, tautomers are really the relationship of a hydrogen atom in a substructure of the molecule. So I would say that's a 1-3 relationship from the O to the C. So you can have other like 1-5 type shifts, 1-7, that type of thing. The keto form, so keto, that's favored due to if you compare the bond strengths of what's making and breaking. So that's the ketone form. The other one's called the enol form. So alkene with an alcohol is called an enol. And so there we see our so highlighted in yellow there, that's the acetone. And then the green is the substituted product. So you've taken acetone, removed an H, and then substituted it for something else. But again, so that if that was an alpha carbon, the carbon next to it is the beta carbon. So really you're looking for 3 carbon atoms that contain the carbonyl as a ketone. And then you should be able to think about using this process to make any sort of product. Questions? So the acetoacetic acid synthesis is used in the preparation of substituted acetones. Given the substituted acetone shown, what electrophile was used in its synthesis? C. So when we look at that, let me highlight in yellow. So there's the 3 carbons of the acetone. So there's the alpha carbon. That's the beta carbon. So that's the bond that we make through the SN2 reaction. So the green part here so that has to come from the electrophile, and then that beta carbon has to have the leaving group. And then we'll just put some nomenclature there. So that's alpha and that's beta. So really it's these reactions we learned today, it's about recognizing the pattern of where these things start from. What bond disconnections do you want to make? But again, the take-home message is look for the alpha and the beta bond. So same concept. There's a substituted acetone in that molecule. Now you're doing a dialkylation. So the electrophile has to have two leaving groups. What should we use for this? B. So there's the 3 carbon for acetone. And then in green, there's the electrophile. So there's alpha, and now you have beta and beta. So both beta carbons have to have a leaving group. So remember the active methylene, methylene means 2, so CH2, both of those H's can get substituted. And again, what's nice about this is, that this molecule, even though I gave it a more formal name, this is also called ethyl acetoacetate. So if you're bored and you want to take a walk to my lab, I can show you how much of this I have. I have like a 20-gallon drum of this stuff in my lab. You can get it for like $50 for like 20 gallons. It's really cheap. And then you can use any SN2 nucleophile that's readily available. So these are really easy reactions to run. And then you're increasing the complexity quite a bit. So now related to that, but a different starting material, is called the malonic ester synthesis. It's called that because what you're starting with, not what you end up with. So in this case, we're actually starting with diethyl malonate. So the ethyl part refers to the esters. The malonate is the number of carbons that have the carbonyls. So diethyl malonate has the two acidic alpha protons, H and H. We're going to use the sodium ethoxide to deprotonate. That now generates our enolate. And then we can substitute one of those H's for R1. So if you look at what you're left with here, you know, you're at oxidation state 3 and 3, and this is going to proceed just like the other one, where we cleave off one of those carbons. So if we cleave off a carbon, eventually what we're going to end up with is a substituted acetic acid. So highlighted in yellow, so the 2-carbon acid is acetic acid, and there's your substitution. So now you're looking for basically a carboxylic acid where you form the bond between the alpha and the beta carbons. Any questions? So that once you do the SN2 alkylation, the last two steps are the same. So sodium hydroxide, that's the saponification. Now what you end up with is this dicarboxylate. And so that gets protonated. So you have this diacid. That will then decarboxylate, tautomerize, and then you have your acetic acid. So really, maybe I can put a warning on there. As long as your beta carbon is sp3 hybridized, you can make any carboxylic acid. If the beta carbon's sp2 hybridized, then you can't do this because the alkylation proceeds through SN2. So that's the pattern you're looking for. Really, when you're trying to figure out what the electrophile is. Because you're always going to start with this diethyl malonate for the enolate part. So the malonic ester synthesis creates substituted acetic acids. What electrophile was used in the preparation of 3-phenylpropanoic acid? I heard a B, or am I imagining that? So it's A. So here's the alpha, there's the beta, the acetic acid part in yellow, then the electrophile part in green. So you have that ring, nothing's happening at this ring. Then you have a carbon, and that carbon has to have a leaving group. So B is not correct because it's not a benzene ring. C and D both lack that extra carbon. But as I said, see that carbon bearing the bromine? That's sp2. So can't. So those type of carbons do not undergo SN2 reactions. Like that said, it's beyond what we'll learn in here, but with other things in the reaction, you could still make that bond. So like a palladium catalyst could form that bond. You just can't do it under the conditions listed. Questions? So I guess just to recap, so ethyl acetoacetate gives substituted acetones. And then diethyl malonate gives substituted acetic acids. And so we've talked about oxidation states. So again, ketones at 2, acids at 3. The whole point of those two reactions really is the increased acidity of that CH2 group allows you to control the enolization of the alpha carbon better. Because ultimately you're extruding out the CO2 and it's almost traceless in a sense. Everyone good? Still see some writing. Okay, so that was two reactions based on alkylation. Now we're going to switch gears and look at a new type of reaction, an addition reaction. So again, alkylation really is substitution. Now what we're going to look at is the product of an aldol dehydration undergoing a subsequent addition reaction. So this first reaction shown, that was the aldol. So if we take acetaldehyde under base conditions, we end up with that beta hydroxycarbonyl. And then if we coax it a little bit more with heat, we can do an elimination where we're losing H2O. So again, we have an alpha hydrogen that can be abstracted, and then we do an elimination. So formally, we're losing water across the alpha and the beta carbons. And that generates an alkene. So an alpha beta, so alpha beta unsaturated. in this case aldehyde. And those are called enals. If you remember from way back, the start of the semester, we talked about conjugation. When you have two or more double bonds, like directly bonded to one another, they have this resonance. You can draw these resonance forms. And so now that one of those double bonds is a carbonyl, it's going to allow us to functionalize the beta position due to the resonance forms. Because remember, up until this point, we're always talking about alpha carbon acidity. And then the beta carbon was coming from an electrophile. So now we can utilize the carbon-carbon double bond of this unsaturated system in a new reaction. So to understand that, let's look at that enal. And we see that, as I'll highlight in green, if we look at resonance forms, if the electrons from the pi bond migrate up to the oxygen, that puts a formal negative charge on the oxygen, a formal positive charge on the carbon. We have this double bond next door. So this is an allylic cation. And that can undergo resonance, where the pi bond moves over, and then that plus charge shifts over to the beta carbon. So in one sense, you can think about the structure in the blue box, how the charge is related. So we know that from the alpha carbon, we can generate enolates. But now, due to resonance, that beta carbon is positive, so it's an electrophile. So synthetically, we can use that to our advantage in a new reaction. So it's called an addition. Something's going to add, a nucleophile is going to add to the beta carbon. That's going to generate an enolate, and then that enolate will react with an electrophile. So our charge affinity based on the resonance, oxygen negative, carbonyl carbon positive, alpha carbon negative, beta carbon positive. So these type of systems are called Michael acceptors. So the reaction is called a Michael addition. So the nucleophile is a donor, a Michael donor. Questions so far? So one of the most common ones, we can take that starting material diethyl malonate because we know those alpha hydrogens are acidic. And then with sodium ethoxide, we can deprotonate one of them. So I'll draw the sort of product of that. So now that's a nucleophile. This negative charge will attack here and then push electrons onto that alpha carbon. And so that's an enolate. We have a proton source in terms of ethanol. So that will do an acid-base reaction. And then at the alpha position, we end up with H. So overall, from the diethyl malonate to the enal, see how that has two H's? You can think of just one of them migrating over to the other alpha carbon. So we call that atom economy. All of the atoms in the starting material end up as all of the atoms in the product. And so now the active methylene, that CH2, it ends up as the gamma carbon. So in blue, remember I talked about these functional group relationships? If we count, say we count starting here as 1, and then we count over to the ester. The carbonyl carbon is 5. So whenever you have that relationship between carbonyls 1 to 5, you can make that through a Michael addition. A Michael addition is also called a 1,4 addition. So those are just terms that are used in the same manner. In terms of the nucleophile, Michael additions are typically run with weak nucleophiles. So potassium cyanide, we just saw enolates or neutral compounds such as amines, alcohols, or thiols. So what's the comparison? Say you had a Grignard reagent. That would be a strong nucleophile. So those typically would not undergo a Michael addition. That would undergo an addition just to the carbonyl of the enal. So that's your normal addition you're used to seeing that forms an alcohol. That's called a 1,2 addition. So weak nucleophiles do 1,4, strong nucleophiles do 1,2. So what are common Michael acceptors. If we highlight in green, so the green, the alkene's common amongst all of them. And then what is different, I'll highlight in yellow. Those yellow groups, we say they're electron withdrawing groups. So we saw that back with the aromatic chemistry. And so for an acceptor, you basically need an electron deficient alkene. So probably not so much nowadays, but this is like this mechanism. I showed you an ionic version, so a lone pair of electrons moving. You can also do this with a single electron called a radical. And so this is kind of classical polymerization chemistry. So these things could be considered monomers. And then the nucleophile would be considered an initiator. So for example, this molecule here, ethyl acrylate. Can you think of an example where you might have used that in everyday life? Say again? So nail polish, probably not. I mean, nail polish remover is acetone. But like super glue or Gorilla Glue, those have a polymer in it that are initiated by moisture. So when you think about it, if you get some on your fingers and they stick together, it's the moisture on your skin that's initiating a polymerization that cross-links your fingers. So just to briefly show you what that means. So a really cheap example here. So you can imagine this just continuing for a long time, but so the initiator would add, and then that negative charge ends up on the alpha carbon, but then it could add to another one. And so as you grow that out, that's the polymer chain. And then within that, you have a repeating unit. So, you know, there's polymer students in the class. This is, again, a very classical reaction, nothing fancy about it. Nowadays, what people want to do is, if we look along this backbone here, this carbon backbone, you can see these relationships of just like the ester groups, so 1, 2, 3, 1, 2, 3. You want to control things like that. You want to control the nature of the side chains, then the stereochemistry of the side chains, whether they alternate So towards you, away from you, all towards the same side, or a section one way, a section the other way. And so there's different names for those things. So does anyone know what raft means? What's it mean? So there's raft polymerizations. They call it like living polymerizations. You can design these functional groups that will like self-immolate. You know what that word means? Like when someone's pissed off and they set themselves on fire. So the side chain will sort of degrade in a specific way that you can control it and like stop a polymerization at a certain chain length. So a lot of that comes through the fundamental understanding of how these functional groups react. So which of the following is not a Michael acceptor? So A is not. So again, for a Michael acceptor, the beta carbon has to be electrophilic. For A, we can show a resonance form that looks like that. So the point here is, as I'll highlight in red, no, maybe I'll do it in yellow. That alcohol is an electron donating group to the alkene. All of these other alkenes, highlighted in green, they have electron withdrawing groups attached to them. So that's the main difference in the nomenclature. Questions? So you ever go to like a buffet? You pay like $15 and you can pile as much stuff on the plate as you think you can eat. So organic chemists are kind of like that. It's like, here's a bunch of reactions. I want to do something else. I want to pile something else on there. So the last reaction we'll see today is called the Robinson annulation. So Robinson was the guy that came up with this. Annulation just means you're forming a ring. A Robinson annulation is two reactions in one sequence. It's a Michael addition followed by an aldol dehydration. And it forms a specific substructure that you can look for to say that that came from a Robinson annulation. So let's look at these two starting materials. So let me call them A and B. So A has a 1,3-dicarbonyl. And so it means that hydrogen is acidic, so pK of 10. So that's the most acidic hydrogen of that molecule and then the other coupling partner B. Now when we look at B, that's called methyl vinyl ketone, MVK. That's a Michael acceptor. So the first thing we're going to do is a Michael addition. So I'll draw that product. And then once that's formed, that's going to do an intramolecular aldol. So here we have alpha beta. So if we deprotonate that acidic hydrogen, we would get that sodium enolate. That can do a Michael addition. So I put 2 arrows there because the resultant enolate gets protonated. Now, when we look at that molecule, there is a boatload of alpha carbons. So there's one, and then these 2 here, they're equivalent, so I'm just going to draw them both in green. So you have a bunch of alpha carbons that can enolize, then you have carbonyls they can condense onto. We're going to ignore the ones in green, which I'll explain after we go through why it happens a certain way. Say we deprotonate from the red alpha, and let's then count over to a carbonyl group that's in the 6-membered ring. So 1, 2, 3, 4, 5, 6. So from that alpha carbon to that carbonyl, or that one, they're the same, that's 6. Then we do the same for the blue. 1, 2, 3, 4. So I'm kind of asking you an obvious question, because the product's shown. What color or pathway do you think is preferred? The 6. So the 6-membered ring is preferred because that has the least amount of strain. If you form a 4-membered ring, now you're compressing the bond angles, and that has strain. So what happens is that alpha carbon enolizes. We see an oxidation state 2 functional group, so it attacks it to give a beta hydroxy ketone. And then we lose the elements of water across that alpha beta bond. So it's a Michael addition, then an aldol, and then really what you're forming, the pattern that you're going to look for so a 6-membered ring, that's an enone, so an alpha beta unsaturated ketone. And then you have to think about how you're dissecting it. So within there, so that dissection comes from the Michael. And then we know that for alpha beta unsaturated, and that's the aldol dehydration. So put another way, all this stuff over here can sort of change based on whatever you're starting with. I got a slide for it, but I kind of already did it. So take a look at that target. And then for each choice, you have a donor and an acceptor. So what donor and acceptor will get us to that target? C. So again, it's sort of pattern recognition. If you look at the target, this is where you're sort of cleaving. Because you're identifying the aldol dehydration bond disconnect, the Michael bond disconnect. Of that 6-membered ring, two of them come from the donor, and then 4 of them come from the acceptor. So as I said, as we approach the end of the semester, this is, do you know what lecture number this is? 21. How many lectures do we have? 27. So we're almost done. A lot of these reactions are just referred to the investigator that studied them. So, when you say the Robinson reaction, if you had no context, you wouldn't know what that is. You know what I mean? So like Robinson, Claisen, Diels-Alder, you have to know the functional groups involved, what are they producing? So there's a lot of information embedded in that name, Robinson. So shown is a target, and then A, B, C, or D is the starting material. So which starting material, A, B, C, or D, when treated with sodium methoxide gives the target? So when we look at that carbonyl, so I could call that a 1,3-dicarbonyl. Or stated another way, there's the alpha carbon, there's the beta carbon. The beta carbon's at what oxidation state? So it's at 2. We're making an alpha beta bond, right? So if it's at 2, it has to start at what? 3. So when we look at the possibilities, what choices can we eliminate? So we can eliminate A and B. And then what C or D best matches the product? So C. So here's your alpha carbon, there's your beta carbon, and it started at oxidation state 3. So that's an example of a Claisen reaction. So as you think about preparing for the final, if you look at the choice D, it's got some extra crapola hanging off here that's not in the product. So there's an extra carbon that should raise a red flag in your mind where does it go? I mean, it doesn't disappear. So your chemical spidey sense should start tingling at that point and say that can't be right. So the oxidation state analysis should help you, and then just simple counting of carbons can help eliminate some derailer responses as well. So we got about 15 minutes left. We'll wrap up with some questions here. So the molecule shown is a steroid. Steroids have this like four ring system, this nucleus. So it's 6-membered, 6, 6, and 5. So I've highlighted 4 carbon atoms, A, B, C, and D. And the question is, when you heat that up, which one is going to lose an acid group based on the mechanism we saw earlier today? So D is the correct response. So D is the only one that's a beta carbonyl. So it's the only one that can achieve that or has that relationship where you can do that decarboxylation. The other thing that's, again, weird about A, B, and C, they're all, for the most part, the same. D is the only one that has a different relationship between those functional groups. So which pair of compounds, when treated with base, would generate the given product? Based on the functional groups you see in the product, how would you sort of classify that? What reaction mechanism is it proceeding through? So an aldol dehydration. So the aldol product is a beta hydroxycarbonyl. When it dehydrates, it loses water. And so if we highlight that carbon. So it's one carbon, right? And so before it dehydrates, it has to be an alcohol. But then ultimately it's starting from an oxidation state 2 electrophile. So with that information, can you eliminate any choices? So we can eliminate A, because there's no carbonyl. Then based on the alpha carbon of the target, can you eliminate any other choices? So B, see, this is an aldehyde. There's no alpha carbon. And so the correct response would be what? C.
So we can have an aldehyde here. We can have a ketone here.
So if I highlight that carbon in green, it comes from that carbon. So that's alpha, that's beta. So the aldol product itself would be that. And then that loses H2O. So we have 8 or so minutes left. Just a brief sort of application of all this to see how it's relevant. So this was my PhD advisor, David Hart. And so I think maybe in the mid-'80s, he had a student, Dwayne Burnett, who went to work for Sharing Plow, which was eventually acquired by Merck. And so while Dr. Burnett was in Hart's group, his doctoral thesis was on ester enolate. So you're generating an enolate from an ester and then condensing that with an imine. So remember, an imine is when you take a carbonyl, you condense it with a primary amine, you get an imine. So you have a nucleophile electrophile. And so this pair of reagents, when they react, will form a beta-lactam. And so that's a common substructure in a lot of pharmaceutically relevant molecules. So Dr. Burnett basically used what he studied in graduate school in his industrial job towards a molecule that's a commercial drug, ezetimibe, and that's used to treat high blood cholesterol. And so this is an example of like an actual billion-dollar drug. That's what a lot of pharmaceutical companies shoot for when they're developing a product. When I say $1 billion, I don't just mean a billion. Like when it's launched, I'm talking like 10 or 20 billion a year. So through that profit generation, they're allowed to recoup any research investment they've put into these projects. So this is an application of sort of what you've learned to a molecule that can treat, maybe we'll call it a lifestyle sort of disease when you get high blood cholesterol. So that's the structure. And so if we look at it, these carbons I have numbered, that 4-carbon ring. So that's an amide. And so this is called, so there's an alpha carbon, there's a beta carbon. Because it's a cyclic amide, it's called a lactam. And then it's a beta lactam because it's a 4-membered ring. So it's anti-hyperlipidemic, and that's the core. And we're really focusing on that lactam in terms of the bond polarity. So if I can point some things out, we know that carbon's at oxidation state 3. So we learned in module 3 about nucleophilic acyl substitution. So we can imagine that carbon, if it comes from an ester, we can split that bond. We can have an amine attack the ester to make an amide. And then throughout this module, we've seen how to make alpha-beta bonds. So in one pot, you can take an ester enolate and react it with an imine, just using the disconnects we've talked about. So in terms of a retrosynthesis arrow, this arrow right here in the middle, we're splitting the molecule in half. So there's our alpha carbon, there's our beta carbon. And we know formally that we can form a negative charge there. And just like with carbonyls, the sp2 hybridized carbon of an imine is electrophilic. So that enolate can attack there. This bond cleaves and puts a negative charge there. It swings back around and attacks that. Now the challenge of this, see the stereochemical relationship there? We would say since they're on opposite sides of the ring, they're trans, is really controlling that. So you don't want the cis, you don't want the other trans enantiomer. So there, you have to control that. And then if we further look at that ester, so we'll count here, starting from the ester carbonyl 1. So 1, 2, 3, 4, 5. That will ultimately get us back to the Michael addition that we learned today. So this thing you can think backwards as coming from the reduction of a ketone, so that gets us to there. And then we're going to make that bond disconnect through the Michael addition. So there's the ethyl acrylate, that was pretty cheap. And then there's ways of making that. So it's what? A Claisen product. So that bond is a Claisen. And then how do we make the imine? So that comes from the amine, and then that comes from the carbonyl. So an aldehyde, and then this aniline derivative. So overall, I mean, seriously, just through chemistry that you've learned in Organic 1 and 2, it's done on an industrial scale. Again, the only probably complexity to it is just controlling the stereochemistry. So with that, we're about out of time. In 1 minute and 45 seconds, your exam will open up. Make sure to take a look at it and do it. Submit it.